So let's think about another kind of algorithm that's not at all obvious at first, but another kind of algorithm that could do somewhat better. And so this is one of many algorithms for the TSP that's based on first finding a minimum spanning tree, of this. Okay, so let's motivate this a little bit. So suppose I've got some graph, and I've discovered a Hamiltonian circuit. Right, so there's my Hamiltonian circuit of the graph. And now suppose I delete an edge. Okay, so I come along here and I say, I don't like that edge. You're gone. Now what do I have? I have a spanning tree of the graph. Okay, it may not be a minimum spanning tree, but it's a spanning tree. Okay, and we know that it's possible to find a minimum spanning tree fast. So here's the idea of the MST-based algorithms. Is first what we do is we find an MST, right? We go find some subset of edges that has minimum cost and hits all the edges. And then we come up with some procedure for converting that MST into a Hamiltonian circuit. And it turns out that if our graph has the triangle inequality, like if it is a Euclidean graph, then when we do that conversion to a Hamiltonian circuit, then we end up with something that has to be somewhat close to the best Hamiltonian circuit. Okay, so here's our idea. 1, find an MST. 2, convert by some means to Hamiltonian circuit. 3, profit, right? So 3, what we say is this Hamiltonian circuit, like we have to argue that this Hamiltonian circuit is somewhat close to the best Hamiltonian circuit. So argue this is close to the best. All right, so let's see how this works on an algorithm called twice around the tree. So here's how the twice around the tree algorithm works. So this is called twice around the tree. Okay, so 1, find an MST. Right, we already know this is you can do this in polynomial time, right? Use Prim's algorithm by one of its implementations, or Kruskal's algorithm, and if you've implemented it well, this is a fast algorithm. So 2, we traverse the MST using a depth first search. So traverse MST with DFS. Okay, as you traverse it, you write down the nodes that you visit in order. Right, write down nodes visited in order. Okay, then 3, what do? You create a Hamiltonian circuit by walking down this list and just skipping stuff that's repeated. Okay, so we'll illustrate this in a second. So we create Hamiltonian circuit by walking down the list, right? This list that was generated by the DFS, and then just skip repeated vertices, right? And so what you could also rephrase this by saying the DFS will backtrack occasionally, right? It'll jump back to nodes after it finds the end of a chain, and so when the DFS backtracks, just create a shortcut, right, to generate your Hamiltonian circuit. Walking down list, so we could say skipping repeated nodes, or shortcutting the backtracks. Shortcut backtracks. All right, let's see what this looks like. Okay, so let me work an example. So suppose we have this graph. So this graph is similar to. I'll put that up there. Maybe that's readable. So this graph is similar to the one I looked at earlier, except I've changed it to be Euclidean. So I am requiring that my graphs are Euclidean now. Okay, so there's 2. So one MST is the following. I shouldn't say one MST. The MST is the following. So it is these edges. 1, 1, 1. Okay, so there's our MST. So now what do? We traverse this MST using a depth first search. And so what that means is we start here, we walk down there, we walk down there, and then when we get to the end, remember DFS backtracks, right? It has to pop everything back off the stack. So as we backtrack, we go back down like this, and then we return to the start, right? So let's put some arrows in to be clear about the direction that this thing is going. But that's that. And so let's just write down the list that was created as we were doing this. A, B, C, D. Okay, so our list of nodes is A, B, C, D, and then C, B, A, right? Just backtracks all the way back down. C, B, A. So what's the Hamiltonian circuit that's created? Well, we go A to B to C to D. And then, C is a backtrack, right? So C is already in the list, so we skip it. B is already in the list, so we skip it. And so then we just jump from D back to A. Okay, and the Hamiltonian circuit that we result in is, it looks like this. I have just enough space to draw it right here. So it's these nodes. So it's A, B, C, D. So it's actually the same one that the local greedy algorithm would give us. This isn't unique, right? It's not the only solution that the Hamiltonian, or that the twice around the tree algorithm could give us, but it is one of the solutions, one of the possible solutions. This one turns out to be an optimal solution. Okay, as just for the sake of seeing other ways this thing could go, let's initialize our DFS somewhere else. So we could initialize our DFS, for example, at B. So let's do this. So there's our MST. Again, it's still the MST. So now what happens if we initialize the DFS at B? So init at B. Well, then we start at B, and then let's just say we break ties alphabetically. So we go B, and then to A, and then we come back, right? We come back to B, and then we follow this all the way down here, and then we come back. Okay, so we can't really tell what the order of the nodes is going to be until we write down the list. So let's make sure we write down the list. So, whoops, that's not A, that's B. So we've got A, B, C, D. So we began at B, and then we went to A. Then we came back to B, then we went to C, then D, then C, then B. Okay, so what's the Hamiltonian circuit? Well, the Hamiltonian circuit says we'll include the edge from B to A, and then we'll skip that second B because we've already been there. So then we'll go from A to C, then to D, and then we've already been to C, so we skip that and jump back to B. And so if we draw this thing out, it looks like this. We've got B to A, and then A to C, C to D, and then D back to B. And so what's the cost of this one? Well, the cost of this one is 6, right? So we've just added 1 to the cost of the other one. So this one, by the way, this was a cost of 5, right? And this one is a cost of 6 total. Okay, so both of them were close to the optimal tour, but this one has no really bad tour, right? There just isn't a way to be terribly bad on this. So in a general sense, we should ask, how good is this algorithm? Well, it turns out this is a 2 approximation, right? So here's our theorem. 2x around the tree is a 2 approximation. For the Euclidean TSP. Okay, so let's consider why. So here's a proof, and this proof is going to be relatively formal, but it's pretty simple. All right, so here's the proof. And for some terminology, let's assign some symbols to some things. So let's say S star. We'll define S star as the optimal tour. Right? So this is the optimal answer to the TSP. Right? Optimal tour. And now let's define SA as the output of the algorithm. Right? And what is it that we're trying to show? We're trying to show, so we want to show that 2 times the cost, or the weight, the total weight of S star is greater than or equal to, whoops, watch what you're doing, Brown, is greater than or equal to the cost of SA. Okay? In other words, we want to show that if I take the cost of SA and I divide that by the cost of the optimal tour, that's no bigger than 2, right? That the algorithm doesn't give me anything that's more than a factor of 2 times optimal. Okay, so that's what we want to derive. We want to derive that inequality up in the upper right. Okay, so here's what we're going to do. We're going to say take S star and remove an edge, right? Remove edge from S star. This creates a tree T. Okay, T is a spanning tree. It may not be a minimum spanning tree, but it's a spanning tree. Right? So that's a spanning tree of the original graph. Okay, and we know this because S star is a circuit, right? So remove an edge and that, or it's a Hamiltonian circuit in particular. Remove an edge and you have left a tree because now there's no cycles, and that tree includes every single node. Okay, and then what we'll do is we'll find a minimum spanning tree. All right, so we're going to say T star. We'll define that as our minimum spanning tree. Okay, so let's relate the cost, or the total weight of S star, of T, and T star. So first, because we took S star and removed an edge to create T, it's clear that T has a lower cost than S star. Okay, so this is obvious from step 1, right? That the cost of S star is greater than the cost of T. Okay, and so if I number these things, I'm going to say this is because of step 1. Right, and then the minimum spanning tree, so T is a spanning tree, T star is a minimum spanning tree, so that means T star can't be any more costly than T. They're both spanning trees, and T star is a minimum spanning tree. So we have another inequality here. T star, right? And this is because of 2, right? Because of that step 2. So this is clear enough, right? The minimum spanning tree can't have a higher cost than the optimal tour. So now let's figure out how to relate the cost of the minimum spanning tree to the cost of our algorithm's output. Okay, so how does that work? Well, think about what happens when after we create the minimum spanning tree. Right, so suppose we've got our spanning tree, our minimum spanning tree, right? So this is what Prim's algorithm gave us in the middle of our working on this thing. So we've got a minimum spanning tree. Now what do? Is we walk around it twice. So we double the cost of the minimum spanning tree, and then we take some shortcuts. Okay, so there's twice the cost of our MST, right? This is when we walk around the whole thing and then walk back, right, by the DFS approach. So now we've got twice the cost of our minimum spanning tree. And then what do? We take some shortcuts to create SA, right? So now in the end, we've got SA, right? We've got this Hamiltonian circuit around the graph. And we know that since the graph is Euclidean, taking shortcuts can't increase the cost. So this inequality goes in that direction. Okay, so what do I have altogether? Well, I can write this as 2 times W of S star is greater than or equal to 2 times W of T star. Right, that's just these two, and then doubling the inequality. Right, that's what that is. Okay, and then I've got that 2 times W of T star is greater than or equal to W of SA. W of SA. Okay, and so in the end, what I have is 2 times the optimal tour cost is greater than or equal to the output of the algorithm. as desired. Okay, that is the 2 times or the twice around the tree algorithm is a 2 approximation for the Euclidean TSP. Okay, so I like to show this proof because before you see something like this, it's not at all obvious how you would actually determine that you're close to an optimal solution without knowing the optimal solution itself. And the way it works in these proofs for these approximation algorithms is you don't go try to derive the optimal solution. You say, I know there's an optimal solution, so let's figure out a clever way of relating that optimal solution, the known to exist optimal solution, to what I know about what my algorithm creates. And usually it takes the form of some chain of inequalities like this, where we say, look, I know how to relate the optimal solution to a minimum spanning tree. And so now as long as I can relate the minimum spanning tree to the output of the algorithm, I'm done, as long as my inequalities point in the right direction.